Hello everyone. So in the previous class, I did told about polynomial regression. So I introduced the topic regularization, less so enrich. Okay. So in polynomial regression, I need to show you the implementation, how to use it. What we have studied in polynomial is if you are having a relationship between dependent and independent in this particular format where the degree of the feature is polynomial, then in this particular case, if we try to fit a line, definitely we will fail because the points which are captured in this equation doesn't suits to be fitted on a line. Therefore, we do apply polynomial regression. And it is not a separate algorithm or a separate technique. I told previous class also. Instead, we have to define degree in linear regression only. Okay, there is no separate algorithm built for it. We have to define degree in linear regression only. How? Let me show you a code for it. Okay, so here is I'm sharing my entire screen, and you can see the code. Okay, so before that I want to talk something more about polynomial. It is a type of regression analysis used to find the relationship between dependent and independent variable of nth degree polynomial. This is non-linear relationship. Here we have to choose the degree. Okay, here we have to choose a degree. That means you have to mention from your side that whether degree n equal to 2 is suitable to find the relationship between x and y, or degree 3 is suitable to find relationship between x and y. What could be the value of n suitable to find the relationship between x and y? Okay, so choosing the degree, that is a crucial part in polynomial regression. A higher degree can lead to overfitting, while a lower degree can result in underfitting. So, by performing cross validation technique, we can select the appropriate degree, what it could be. However, in this particular case, the example which I am giving you, I will be putting a degree n equal to 2 to show you how it works. In cases of multiple polynomial features, multicollinearity may exist. That is an issue. For example, if you are having y equal to beta naught plus beta 1 x1 square, beta 2 x2 square, and they are showing multicollinearity, then that's an issue. Okay, because that's one thing which is responsible for overfitting in a model. So multicollinearity is an issue that can destabilize the coefficients beta 1, beta 2. interpretability. That means higher degree terms calculation is tough. Lower degree terms calculation is easy. For example, we did solve so far using linear regression for n equal to 1. But if the degree becomes higher, then solving for the coefficients is obviously complicated. Okay. Therefore, it is saying that interpretability for higher degree polynomials is complex in nature. Anyways, the application of polynomial regression is in economics because economic indicators may not be linearly related. In physics, also to describe the trajectories and the curves. In biology, also to deal with the growth rates or population dynamics. Okay, and here is the implementation. You are going to take linear model only, linear regression. Polynomial features will be taken from sklearn pre-processing. Okay, so model will not change. Instead, we will take polynomial features. Let us suppose this is your data and this is the target. Okay, and we are checking whether polynomial relationship of degree 2 exist in the data or not. Okay, so polynomial features degree 2, poly dot fit transform, this is part of pre-processing. Poly dot fit transform. Okay, so what we got from here, let me print each and everything one by one. Let me first print x, the data which you are taking. Let me print y, the output which we are taking. These are the array. And here, let me print what you got after fitting. Okay, let me print the predictions also. After model training, what you got. Okay, and here is. Hmm. So, this is your, I think I printed x. So, the values of x, this is our, okay, this is a small x. I think I made a mistake. Now, 1, 2, 3, 4, 5. These are the inputs which you have given, and these are the outputs which you are expecting. So, this is x, this is y. Next is you performed transformation of x in a polynomial of degree 2. So what happened? See, this is 1, na? 1, 1, 1. That means if I take 1 square, so it will be 1 only. Then 1, 2, 4, 1, 3, 9, 1, 4, 16, 1, 5, 25. So what we did here? We performed the square of the terms. 1 ka square is 1, 2 ka square is 4, 3 ka square is 9, 4 ka square is 16, 5 ka square is 25. This is what we have performed. Okay, so number and its square. Now it will behave as my data. It will behave as my data. After transformation, that will be my data. And I am putting this transformation into linear regression. The transformed data I am putting into the linear regression. This data will be put into a linear regression where a target is this again. This is my target. Okay, this is my target. And what happened is I printed prediction also. And my model predicted exactly correct. 2, 8, 18, 32, and 50. This is what my model predicted. See, I plotted also. So these are independent variables. 1, 2, 3, 4, 5. These are the values. This is dependent variable till 50. And this is polynomial regression fit line, blue. And red are the data points. What data points they are? 2, 8, 18, 32, and 50. Okay. So my x comma y prediction, that is a polynomial regression fit. That's a line. See, between this point to this point there is a line. This point to this point is a line. Point to point is a line. It's not a curve. Understand? It's not a curve. It's a line. Between every point to every point, we are not making like this, just connecting like this. Okay. This is how we call it as a term curve linear. This is called as curve linear. The overall, if you see it, it looks like a curve. It is made by linear or the lines. This is called as curve linear. So, in a practical approach, as I told, we do not have any polynomial regression separate. Instead, you are available with x, you are available with y. You first tried linear regression, but you failed to got the answer. You failed because the patterns, the relationship were not captured. You failed. Then next what happened is you tried that there might be the features which are showing polynomial relationship. So you took poly features with a degree 2. 2 is your assumption. Okay. 2 is your assumption. You can assume 3, you can assume 4. 2 is just your assumption at this moment. So you said that okay, I am currently having polynomial features of degree 2. Highest degree is 2. So this is kind of a polynomial. This is kind of a polynomial I am having currently. So it's like this. You said polynomial features equal to 2. That means it hypothetically create an equation like this. It will create an equation like this. X1 square only, because you are having only one feature x. And what it will do, okay, here the coefficient, okay, let us suppose just focus upon these only. Okay, focus upon these only. So it will be like, okay, here the coefficient, just take it as 1 dot beta naught, beta 1 x1 plus beta 2 x1 ka square. So your polynomial feature, this the step which I mentioned, will create a hypothetical equation of degree 2, highest degree 2, and it will fit your x values inside it. The x values are 1, 2, 3, 4, 5. Okay, so here it is 1 already, the coefficient. This one will come in x1, it will become 1. This one will come in 1 square, it will remain 1. Now, this one as it is. 2 will come here, so it will be 2. 2 will go into square, it will become 4. Then, okay, 1, this one will remain as it is. 3 will come here, so it will be 3. And 3 will come here, it will become 9. Same for 4 and 5. So 1, 4, 16, 1, 5, 25. So because a polynomial equation is created, you transformed your data into a poly equation. Okay, that's what you did. Okay, and now since you are having this polynomial data, it doesn't matter. You did a very smart step. Initially, you don't have any linear regression present in linear model. No, there is nothing like polynomial model. So what you supposed to do? Instead, you look out for polynomial equation. You put your features inside this polynomial equation. You got a data, new data, and now you are putting this data, that is x poly, into linear regression. That's what you did. That's a smart move. In your linear regression, you are putting polynomial data. Fine, done. That's it. Your model got trained over this data. Next, you can perform the prediction. Then you can plot it, and you got a very good answer. The data is very less, and you got a proper fit over the data. Okay, fine. So this is what you got. Okay, fine. So this is one of the example, one of the implementation which I want to tell. I do have one more implementation available for you to have a better understanding. Now I am taking already available data in sklearn with the name of fetch California housing. This is the data set available with me in sklearn. So in the above example, I created a simple data from my side with X and Y. This is from my side only, a simple data I created. But now I am taking a data set which is present in sklearn, that is California housing data. That is house price prediction data actually. So I fetch that data. Okay, I fetch that data. And then I am taking a feature X from it. Okay, using the first feature, that is medical something, medinc something, there will be a feature. I am taking its value, all the values of feature number 1. Okay, if you want, I can print here. I can print capital X. And if you want, I can print the Y also, print Y. Okay, so colon comma 0 means column number 1. Colon means all the rows present in column number 1. So just take only one feature. You are having your California data like this. This will be your California data. Okay, this will be your California data. This is 0th column, 1th column, 2nd column, 3rd column, 4th column. This is 0th row, 1th row, 2nd row, 3rd row, 4th row. You are picking only this column, this one, this column. Okay, and Then just taking your target, you perform train test split. 20% data you took for the testing, 80% data you are taking for the training. Again you fit polynomial feature. Polynomial equal to 2, you perform fit underscore transform, and then you perform transform. Okay, you have transformed your data xtrain into polynomial. You convert the same way as I taught above, the same approach. You have transformed your data in polynomial. If you want me, let me write a statement to show you. Print x train poly. Okay, so the same approach which you have used above, here you are also using the same, and then you are using linear regression model. You are fitting your polynomial features here, and you are performing the prediction also. You calculated the errors also, MSC and R2 score, and that's what you have printed. Here is your x, here is your y, and here is your x train polynomial. So this is our x train polynomial. Okay, so I have this is your x. I have splitted x into x train and x test. Okay, and the one which I have printed here is for x train. Okay, you can see x train. Okay, fine. So this is the approach I followed. You are having x, y. You took only one feature in x. Target is obviously one. You splitted x into train and test. Sorry, yeah. You performed polynomial n equal to 2 for train, also for polynomial n equal to 2 for test. Okay, and then you have used this data into linear regression for training. Okay, your model got trained, then you have performed the prediction from your model, and then you have plotted the prediction. Here you have plot x test, y test, and x test and y test prediction. The plotting has been done. So the red are the actual values and blue are the predicted values. You can see the density of actual is more, and here also I'm getting the prediction. I'm getting the points which are covering the red points. My mean square error is zero point 0.7, my R2 is 0.4. That means error, you very well know how far the points present away from the line, and R2 is the variance explained. So this is what I got as a result. Now I hope this code will be the reference code for you to apply polynomial regression. Only the part of code is this. Okay, rest nothing. As usual, linear regression you use, they are also here also same. Okay, you can change the degree also. Degree equal to 3, degree equal to 4. It's up to you. You can change it. If you make degree equal to 1, then it will be linear only. Okay, so higher degree terms. So the smartness which we are following is we are creating a equation, polynomial equation. We are putting the value inside the polynomial equation, and we are creating a data with respect to that equation, and then we are putting that same data into the linear regression model. That's what we are doing. No separate polynomial regression algorithm. Just by doing this thing. So the people don't understand. This is still linear regression. This is still linear regression. Sir, you are using linear regression model, sir, for training. So it is still linear regression, not polynomial. You just transformed your data into polynomial. There is no polynomial regression. This is linear regression only. So people get confused. There should not be any confusion. There is no polynomial. You transform your data into polynomial and fit it like linear only. And the curve which you are seeing because of the polynomial points, that means higher degree points, they are looking like that. But if you have a close view to them, if you put a close view, the points will be connected via line. It's not like a straight, like a clear curve. No, they're connected via line. Okay, so that's what it means to be polynomial regression, a very important concept. The people do skip this thing. Okay, so when to apply polynomial, understand what kind of problem statement you are having. Are you dealing with economics factors? Are you doing dealing with the physical factors? Are you dealing with the biological factors? What is your data? So if you are having a domain knowledge, you will get to know that okay, I am dealing with these factors, and if I apply linear regression, maybe I get high errors. Let's try polynomial. Okay, try polynomial and check what is the possibility. Okay, few more things I want to say or ask. See, what you have learned in linear regression is it's been taught to you that this is a line, and you make plot between actual and predicted. You may get a value like here, you may get a value like here, you may get a value like here. So these are errors. E1, E2, E3, these are the errors. Who decided this line? Who decided this line? You say y equal to mx plus c, y equal to beta naught plus beta 1x. Beta 1 is slope. How much is the slope? 45 degree, 30 degree, 60 degree. How much? So how can I make this line? And obviously we are having intercept also. So this line is not like the correct one. The correct line should have to be this. If I consider beta naught as an intercept and beta 1 as a slope, beta 1 as a slope, this should be the line. But beta naught and beta 1 are calculated by optimizing cost function, by differentiating and putting it to 0 by optimizing cost function, that is calculated. Okay, so it totally depends upon the data you are having, x and y. Okay, because you perform now d by d beta not and d by d beta 1. You equate them to the 0. Okay. So this line in general way which is been given to you, and then it has been told that this is a error, this is a error, this is a error, this is a error. This is a best fit line. Best fit line. That means if YA and YP do have a points that totally match here, that is a best fit line. Same points, YP and YA. So you are going to get a line and that is expected to be like 45-degree angle. But that's not the always every time scenario. You may get points above and below that will produce the error. Okay, so we do make this in general context, just general, that linear relationship line. Okay, fine. Also, I just want to say prediction, prediction YP and YA. Aren't we making line between X and Y? Because we are expecting the relationship between X and Y to be linear. Why I put YP and YA here? I haven't told that relationship between YP and YA is linear. The relationship between X and Y is linear. That is what we are assumption. That means every feature in X should be linearly dependent on Y. That's what we are expecting. So is this plot correct? Is this plot correct? If we make between Y and YP, how I can say that this is a best fit line? Okay, fine. These are certain curiosity which is present in my mind because we did not have to be just listening and a lecture has been taught a way to tell you something, to tell you something. No, lecture should be to teach you for exploration. What are the possibilities? If something happened, why it happened? That should be the point. So it comes under your curiosity between whom we are making the plot, why we are making the plot, why it is a line, what angle it is having. It should come under your curiosity. Okay. Well, huh. These are few questions which came into mind in my mind, so I asked to you. You have to give me answer for that. You may get the answer in my lecture only. Okay, just continue with some further topics which I was teaching, and whatever I ask, I will cover them also. Meanwhile, you should have to think. So, in yesterday's class, I did discuss about lasso and ridge regression. Just any question, please say. I would like to use different curve, fit like sigmoidal or exponential. Is that possible instead of polynomial? Sir, I think I haven't seen that n features n features value of n to be something different. I haven't seen. sigmoidal or exponential. Okay, because you are writing a equation in this particular format. That's a good question. That can we have a square root also? Can we have that? It's also not linear, na? For example, if I'm having beta 2 under root of x1, this is also not linear. I can have exponential also. Y equal to beta naught plus beta 1 x1 and beta 2 x2 x3 x2 might be having exponential representation. Yes, there is a possibility. For this, how I can define degree? That is the question. How to define degree? Degree is something which you are writing e key power, x key power, feature key power something, n. You may have exponential relationship. Yes, true. I'm not denying. So how I can define the degree for it in this equation, and how I can write in my code which I have shown. Yeah, here. Is there any way you can write e key power x or sigmoid? For this, I think not possible. Degree 2, degree 3, degree 4. You can try with degree 1.5. Will it work? What is 1.5? 1.5 will be 3 by 2. So if you want me to check it, let's try something. 3.5. Run the code. Invalid parameter. Error. It's unable to take such degrees. The degree parameter of polynomial feature must be an integer in a range of 0 to infinity or an array. Got 3.5 instead. So this is not error. This is information which is given to us. What can we put inside the degree? So I hope, sir, it's now clear. Integer only. 0 to infinity integer. It takes and it will give you the answer. But if you put any floating point or something like that, it will throw error. But I'm not denying your question. Yes, we do have such kind of relationship also. Exponential, sigmoidal also, square root also, cube root also we are available with. They all are not linear. Okay. So maybe you have to transform those into that shape. If you think that, sir, any of my feature is not linearly related, you got a chance. Either, see, you can take transformation. Square root is also a transformation to convert a feature into normal. I've already taught you. Log is also a transformation which will help you to convert a feature in normal. So you can apply these transformations, and you are already available with root of x. If you are available with root of x in your equation, then it's good. Nothing to do, sir. Nothing to do. No need to apply poly. If you are available with cube root, I guess no need to apply poly. Okay, not to apply. If you are having e key power x, something like e key power or something exponential, maybe you can apply log transformation and see how its distribution goes. But for polynomial, they said only integer we are expecting. Only integer we expect. Nothing floating points. No. Okay. So we may have data challenges. That's a good question. We may have data challenges. different features with different relationship. That is why multiple linear regression problem stands. Okay, and coming practically, na, that is working practically on such kind of data will help you to understand better what are the issues and what could be the solution. So, according ultimately, you have to apply linear regression only. You don't have any alternative. So, if you are having any square root feature, any cube root feature, check the distribution. If it is like normal, then keep it directly in LR. No need to worry because LR expects normal distribution. So, sir, you can try. Okay. And yes, I was talking about regulation technique, less so and the rich. Regularization. That is L1 and L2. That's what I was teaching. This is less so, this was rich. And why we are taking regularization? Because of overfitting in the model. Okay. Our linear regression model is subject to overfitting. That is why we need to put penalty. And I taught yesterday in yesterday class, I taught you this distance calculation. A, O, B. I taught you this distance. If you are going to reach from A to B, you have to take this path. That means OA plus OB to get AB. This is called as Manhattan distance. And if you take the shortest path, that is called as under root of OA square plus OB square, that is called as Euclidean distance. Euclidean distance. This Manhattan is L1. Euclidean distance is L2. In what context like this? In this context. If you are having an equation y equal to beta naught plus beta 1 x1 plus beta 2 x2, and if this is overfitted model, L1 for L1 you can take the sum of the coefficients. In L2 you can take sum of the squares of the coefficients. This is L1, this is L2. Some of the coefficients kindly do connect to what I taught. Manhattan. Manhattan distance is the sum of the lengths. However, Euclidean is the shortest distance, this under root. So either you can put under root also. No worries. Under root of the square. So the concept of taking L1 and L2 came from Manhattan and Euclidean only. These are penalty. These are penalty. How to apply? Where to apply? The cost function of linear regression is summation of yp minus y का whole square by n. You have to add penalty to it for giving overfitting. If it is like this, then it is less so. And if it is like this, then it is rich. Where lambda is regularization parameter. It is regularization parameter. And these are the penalty terms. So L1 is equal to beta naught plus beta 1 plus beta 2. L2 is equal to under root of beta naught plus beta 1 plus beta 2 squares करना है, square you have to do. You have to divide your equation by these. So y equal to beta naught plus beta 1 x1 plus beta 2 x2. Divide the parameters by these terms. ये पेनल्टी हैं. If any feature, any coefficient, okay, any feature which is correlated collinear, this penalty will reduce the impact of the coefficient associated with that feature. It will minimize the value of, you can see in a division. What the division do? Division minimizes. So this will minimize the impact of the coefficient. And if the coefficient tends to 0 or it may become 0, so that particular feature will be dropped from the equation. I will be talking more on this because very interesting topic, regularization. Let me put this thing again. I'm sharing it again. Okay, very important topic, regularization. And I hope you understood polynomial regression today. Okay, let me